Hello, my name is Jose Angulo, and I'm here to do a small presentation on resins and matrix technology systems. So resins are used in plenty of applications, especially aviation, and also found in prosthetics and other common household goods. When we talk about thermosets and thermoplastics, it's pretty much just glue mixed into fibers to create a hard object. All right. So the objective of our presentation is to get you guys proficient in mixing resins and using mix ratio percentages, and to be able to properly mix two-part systems given, at the end of the class. All right. We're going to have you answer two or three of the questions correctly, provided information of the thermoplastics and thermoset resins. Okay. What is matrix technology? Okay. The matrix acts as a bond, it's like with the molecules coming together to create something solid, and it encapsulates the fibers and makes that hard, solid object. All right. So selection of matrix and matrix material has a major influence on the shear properties of the composite laminate. So what I mean by shear properties is how much strength it has to pull apart or hold together in different type of stress or environments. Okay, thermoset resins and thermoplastic resins use matrix technology to bond by mixing with fibers and enabling the transfer of loads from fiber to fiber. So, with that being said, if we had maybe a blanket, and the blanket is soft, it moves back and forth a lot, and we add the resin system to it and glue to this blanket, it's going to be hard and rigid. And we can use this type of stuff in applications to build aircraft skins and wings. As far as prosthetics, I really like that part of this type of technology. It's built lighter and stronger arms for amputees, including veterans, and just those common accidents that happen, tragically. Okay, thermoset resins. So we're talking about two different resins, thermoset and thermoplastics. Thermoset is pretty much a resin system that uses a two-part as well as the thermoplastics, but what makes it different, the thermoset, is that once it's set and solid, there's no taking it apart. It is set, it's done, and you cannot reuse it. The part that you made is done. So let's say I'm building a leading edge or trailing edge for a helicopter, and I need to rebuild it, and I set up my thermoset resin with my fiberglass, and I make my repair. Once it's done, it's done. No type of heat or anything but actual physical destruction is going to take that apart. So the cross-linking, it uses cross-linking to join molecules together in a chemical reaction. Once it's locked in place, the resins cannot be melted, as I said before, or reshapen. Thermoset resins typically require time and heat to cure. So basically, when you have the part A and part B and you mix it together, it's going to take time to react. The heat is going to actually bond the molecules together to make it a solid piece. So we have different examples of thermoset is like polyester and vinyl ester, and also epoxy. So maybe your JV Weld or something that you use in the garage to put together like your kid's toy or something that broke. That two-part thing you mix together and it's solid as a rock, that's going to be your thermoset resin. Okay, so we move into thermoplastics, and thermoplastics is the most common thing that we have in the world, pretty much. Almost anything plasticky you can think of comes from a thermoplastic resin. Water bottles, your kids' Legos, your Legos, whatever it is that you think like that is made out of plastic is from a thermoplastic. So it started as a liquid and brought to temperature, and then it's molded into the desired shape. So even if you were tired of that shape, you would melt the plastic down and be able to reshape it. That's the difference between the thermoplastic resin and the thermoset resin. Okay, so the chain molecules, it's a chain molecule structure with no chemical links between them. So the difference between the thermoplastic resin and the thermoset resin is the molecules do not bond in a way that is permanent, right? So it changes from a solid to a liquid when heated and solidifies upon cooling. Thermoplastic resins typically require 300 degrees Fahrenheit before they start to melt. So uh, you say, if it seems easier to make parts and things out of thermoplastics, why aren't they more commonly used in things like aviation or um, prosthetics and things like that? Because aviation, things get up to temperature. You have something by the engine, it's gonna reach well over 300 degrees Fahrenheit. So thermoplastic resins aren't great for aviation use. So that's why you stick to the thermoset, which includes the fiberglass and carbon fiber layups. So the actual epoxy, okay, epoxy is cured by mixing with a hardener. So you have a part A and a part B. So the part B is usually the activator, and it it causes the molecules to reach out and expand and grab and then solidify into something hard. As a thermoplastic resin, epoxy uses cross-linking to make one large molecule structure. Um, if mixed improperly, hot or cold, it may not it may not obtain the desired structure or thermal properties. So when I say whether it's mixed hot or cold, what I'm actually talking about is whether you weighed out the resin system's property, whether you put too much part B or not enough part B, and then it'll lead to the improper setup of your resins, which can lead to a catastrophic failure of your part. All right, so we're gonna get into actual mixing resins, and what I'm gonna want you guys to do is follow along with the actual PowerPoint presentation that I'm gonna include with my video, and we're gonna go through it really quick. But with the PowerPoint, you're gonna be able to reference the numbers and use them in the future. All right, so resins can be mixed by weight or volume. So resin systems must be completely mixed to ensure the proper cross-linking, like we spoke about before. Mixing by percentage and ratio, to me, is the most accurate, other than mixing by volume. So when I say mixing by volume, I mean 1 part to 2 parts. That's what I mean. So if I have a cup of part A, and then I'm telling you put 2 cups of part B, 2 parts of part B, so it's going to be 2 cups of part B, and you mix them all into one. So that's by volume, right? So when we're mixing by ratio, you're always given a ratio, especially on resins, right? So you have, for example, if we have 100 to 25, so 125 talking about part A being 100 and 25 being part B. So we need to find the percentages on to turn into the amount that we're going to be mixing together. So what we're going to do is add the 2 amounts for the sum. So if we have 100 part A and it says 100 to 25, we're going to add those together and make 125. Divide both sides of the ratio by the sum. So if I need a part A, which is going to be larger, I'm going to divide 100 divided by 125, which is going to give me 0.80, right? And then to get the part B, I'm going to divide 25 by 125, which is going to give me 2.0, right? 0.20, excuse me. So what I could do with that information is multiply it into the amount of grams that I need, and it's going to give me the part A and the part B. So so if we have ratios of 100 to 25 and factors by 0.80 and 0.20, right? And so if we needed a complete amount of resin and we need to mix out 24 ounces complete, so what we're going to do is multiply the 24 ounces by the 0.80, because we know that's our part A, and it's going to give us our total. And then we're also going to multiply 24 ounces by our part B, which is the 0.20, and that'll give us the total for our part B. So to make it quick, the part A for 24 ounces is going to come out to 19.2 ounces, and then the part B is going to be 4.8 ounces. Combined together is going to make 24 ounces. So why you would do it like that and not by volume is because a lot of the resin systems are very expensive. So we need to accurately pour out the amount we need without wasting. Like I said, you'll be able to go through my PowerPoint presentation. Unfortunately, I cannot display it at the same time, but you'll be able to look through this and and be able to reference it in the future. It could help. Mixed ratios can also help with mixing in the kitchen and different things like that. You don't have to only use it for resins. It actually is a really great thing to know. Okay, so I want you guys to be able to answer a few questions. Fortunately, I can't get any answers back, but I want you to know what stops a thermoset from melting and remolding. So we spoke about that. The thermosets, the difference between thermoset and thermoplastic, and why thermosets cannot be reset. So you could look back into the PowerPoint, or hopefully you picked it up on the first time around, and see what's the difference between the thermosets and the thermoplastics and why you can and cannot melt them. All right, I want you guys to name an example of a thermoplastic. Okay, we talked about a couple things. Think of something that's plastic, commonly used, that you think you could melt down and jump back up. We spoke about them earlier. Maybe you can think to yourself and answer that one out loud. Like, fortunately, I said I can't hear back from you, but all right. So if a matrix is mixed improperly, what might happen? So if we mix up resins improperly, we spoke about that. What could happen? We won't go back into it. But like I said, you go back into the PowerPoint presentation or just back into the video, and then maybe you can pick up on that before. Okay, in summary, we spoke on matrix technologies, pretty much the very dumbed down version or of molecules. I'm not going to even attempt to say I'm some kind of biologist or chemist to to go into that. But and then we also spoke of thermoset resins, thermoplastic resins, and mixing of resins. So this is my job. This is what I do. I'm an airframe repairer, but I also enjoy using composites and stuff on my free time and making things out of it as a hobby. So hopefully you guys can get a little insight into it and enjoy it yourself. Maybe pick up some cheap resin systems and fiberglass at your local hardware store and get into something yourself. All right, thank you very much, and next time.